So here's a expansion of that table that we saw in the previous slide. This is going to go look at all of the different molecules and all the different kind of displays with multiple electron domains. So the first one is a molecule with 2 electron domains. Now, what that ultimately is going to look like is that is a linear molecule. A good example of that is carbon dioxide. Now, it's important to keep in mind that this is all from the perspective of a central atom. Okay, so we can say with respect to that central carbon, this is a linear molecule because we have 2 electron domains, which is represented by 2 double bonded atoms, so those 2 oxygen atoms. Now, when we grow to 3 electron domains, those electron domains can vary a little bit. We've got Bf3, where we have 3 fluorine atoms surrounding our central boron, or we have NO2 minus, where we have 1 lone pair of electrons and 2 adjacent atoms. Those are 3 total electron domains. However, those electron domains are different. One of them has 3 bonding domains, that Bf3, and no non-bonding domains. Now, you also have so total of 3 electron domains, 2 bonding domains, and 1 non-bonding domain. Now, what that means is that that non-bonding domain, it occupies a little bit more space. And so what that is going to do is that is going to actually more or less press down on the bonding domains and occupy more space, in which case it's not going to be a linear molecule. It's not going to be a trigonal planar molecule, but rather it's going to be a bent molecule. And bent is a structure that we're going to see more and more throughout this discussion. When we have 4 electron domains, we can break that down into 3 different performances, or 3 different options. The 4 bonding, no non-bonding, 3 bonding, 1 non-bonding, and 2 bonding, 2 non-bonding. Okay, so if we have CH4 as our example molecule for a 4 bonding domains, no non-bonding domains, that molecule is a tetrahedral molecule. When we have 3 bonding and 1 non-bonding, we have a trigonal pyramidal molecule. And so what that looks like is this lone pair of electrons has this kind of bulbous shape. It takes more space. Then if we have 2 bonding and 2 non-bonding, that's actually the geometry for a molecule like water. Sometimes you'll see water drawn a little bit like this, where you have lone pairs of electrons basically opposite of those hydrogen atoms. And what that's trying to show you is that these non-bonding pairs, or this lone pair of electrons, they're pushing those bonding pairs of electrons down, so it takes up more space. 5 electron domains, you can have 5 bonding, 4 bonding, 3 bonding, and 2 bonding, and then you have basically however many non-bonding to get you to that grand total of 5 electron domains. Now, what those geometries do is they're a little bit variable. So if you have 5 bonding domains, that molecule is considered trigonal bipyramidal. You have essentially 2 pyramids, one up top and then one on bottom. It's a little bit tough to see, but a molecule like PCl5 would fit that billing. Now, if you have a single non-bonding domain, that would be appropriate for a molecule like SF4. Well, that 1 lone pair of electrons is going to occupy more space. ClF3 is 3 bonding and 2 non-bonding. And then finally, XeF2, that's one we actually have already talked about. That's a linear molecule, but not linear in the same way, or it's a little bit different from, say, CO2, because we have these 3 lone pairs of electrons. Oh, that's supposed to be an Xe. 3 lone pairs of electrons. And then on the opposite poles, we have F and F. Okay, so these 3, I'm going to circle them in green. these three lone pairs of electrons, it's tough to see, but they're on the exact same plane as one another. Again, it's tough to see because you're trying to look at a 2D picture into 3 dimensions. Then finally, 6 electron domains. The observed kind of breakdowns of those are 6 bonding, 5 bonding, 4 bonding, and 6 bonding, 5 bonding, 4 bonding, and then 0, 1, and 2 non-bonding domains. So those, you're going to have something that's octahedral, square pyramidal, square planar. Now that octahedral might seem a little bit weird because it's like, well, there's only 6 things around it. But what that structure does is it produces a total of 8 different faces to that molecule. So imagine that you have, I'm gonna shade them in. So here's a triangle, here's another triangle, there's a triangle on the back and triangle on the right hand side. That's 4 triangles, four faces. So you're making, think about it like a die. Well, here you've got one that has 8 sides, hence why it's octahedral. It only has a total of 6 points to it, but that's a octahedral molecule. Okay. Things to note, things to consider with respect to this: molecular geometries and electron pair geometries are the same only if there are no non-bonding electrons on that central atom. The bonding angle for the molecules are determined by their electron pair geometry. When counting your so-called things around a central atom, every thing counts as one regardless of what it is. And whenever I say things, whenever I use that term things, what I'm talking about are your bonding pairs of electrons, non-bonding pairs of electrons, and so on. So whether that's a lone pair of electrons out here, or it's a single bond, a double bond, or a triple bond to another atom, they're counted basically the exact same. All right, well, I hope this was helpful, and I'll talk to you all later.